Okay, so hello students. I'm quite certain that you all are doing well. We do have a situation where we can't take physical classes, but do need to continue with the course because that's very important, both from a progress point of view and also looking into the picture that since all of you are in your fourth semester right now, these exams and completion of the course is very important for the degree. So I'm going to start with the final unit, which is the introductory cosmology section. Quite an interesting topic, and this will be your first lecture based on a PPT presentation. Before I start with the class, I'd like to tell you that please take note of whatever I am saying because I have not put everything on text. So I'll prefer that you listen to it very carefully, and as and when required, please take some notes. Since this is a video, you can definitely pause for some moment and then again you take the note and then continue with that. So in introductory cosmology, we are going to basically talk about the universe. So what is the nature of the universe? How is that working? It's basically a question for a very long time. We humans basically have no idea what's going on in the universe. To help, we made up stories to either help us explain what we saw or to make us feel better about what we didn't understand. But then science came along and we started to understand. We could test our ideas, and as we got more confident in the process, our ideas grew. The field of cosmology was born. This was born in the late 1920s. It's not a very, very old branch of physics, you can say, in general, or in science. The study of the cosmos itself deals with cosmology. And now, after centuries of speculation and the stories, we can actually have a grasp on the biggest ideas that are what is the nature of the universe. So, let's find out by the turn of the 20th century. Scientists knew that Earth was old, it was really old. In fact, if we look into the Darwin's theory of evolution, it strongly implies that the Earth was at least millions of years old. So I hope all of you know about Darwin's theory. Also, it doesn't deal with physics directly. We're talking more about biology here and evolution of humans, but it does trace back the age of Earth, which is millions of years old. We need to keep in mind that the age of Earth might be millions of years old, but the age of the universe is even older. So, Lord Kelvin, as we all know, was a very respected physicist. He was also an engineer. He confirmed that the Earth was ancient, given that it must have cooled from an initial molten state. That takes a while, at least a million years. How old exactly, no one knew. As for the universe itself, it logically must be as old or older than the Earth. Now, a popular model for the universe was that it was static. It is and always has been as we see it now, and in general hasn't changed. Stars may be born, they might die also, but overall things pretty much stayed in balance. The balance was always there, and the universe always existed. It will always exist, and definitely there are galaxies in it and so on, and there is a variation of idea. But that's what is in a nutshell. So if we just believe or talk about it in a nutshell, we can talk about this in terms of the Big Bang theory and so on. So, in a nutshell, it is what many astronomers believe, that it is important when we try to understand observation in astronomy, we fit them in a framework of understanding things. We think we already know. When something doesn't fit, it is a problem. Maybe the observation is wrong, or maybe we're misinterpreting it, or maybe the framework is wrong altogether. Well, that's a big step to undertake and needs proper contemplation and skepticism. So science is a thread that basically connects the whole thing, but it definitely may need reweaving sometimes, right? Because if some of the theories fail, then we have to revisit on our ideas. So that's very important. This picture is basically you can understand this is basically a picture which is very much cosmological in nature. Now in 1912, there was Vesto Slipher. Well, this name sounds to be very interesting. Okay, it's one of the coolest name probably as an astronomer. I have heard it somewhere, so I'm telling you this. So in 1912, this astronomer started taking spectra of so-called a spiral nebula. You can see that the other picture is basically the picture of a nebula, and he has started taking pictures of those, hoping to get some insight on the characteristics. Now you have to remember that this was well before we understood what galaxies actually were. So before 1912, we didn't have much idea about galaxies, and it actually took him several years of observation. But in the year 1917, he had observed 25 of them, and he found something astonishing when he examined their spectra. He saw that almost all of them were highly red-shifted. So this term of redshift, blue shift, and all is common. I think you have already heard about this when you have done your UV visible spectroscopy and so on in your second semester when we are doing studying experimental technique. It means that there is a shift towards the wavelength of red lights. Okay, so that's basically what is called redshift. So what happened was, in other words, it basically looked like most of these objects were rushing away from us at high speed, millions of kilometers per hour. Now, what that could mean that at this point, two different lines of work began to converge. Now, the point here is earlier people used to debate about, is the Earth expand, or is the universe expanding? Is it contracting, or it's remaining the same? Well, Einstein also had his ideas on these. So at this point, two different lines of work began to converge. One was actually by a Belgian theoretical physicist named George Lemaître. In the year 1920s, he has been actually studying Albert Einstein's work with equations dealing with the behavior of the universe as a whole. Now, Einstein had concluded that universe was static. But Lamech was not agreeing to the fact. He found that an expanding or contracting universe fits the equation better. Now we know that we definitely need to use some equations to understand the physics of the universe. So in order to fit those equations, an expanding or a contracting universe gets a good support from the mathematical point of view. So given the redshifts by Slipher, he proposed the universe itself was getting bigger, which is why the galaxies appeared to be moving away from us. Now there was another brilliant physicist. He was Alexander Friedman, and he had also reached the same conclusion. At the same time, astronomers were trying to determine the distance to the nebulae. They understood it to be galaxies in their own right. So the nebula were considered to be galaxies in their own right. And as we know, Edwin Hubble. So the Hubble's telescope is one of the most popular telescope, taking a number of images of the cosmological universe. And Hubble's expansion is also a very important part that we are going to study. We're going to understand the basic theoretical aspect of this. So Hubble and his assistant Milton were at the forefront of this. They observed variable stars in the Andromeda galaxy. I think all of us have heard about the Andromeda galaxy as the image of the Andromeda galaxy actually. That allowed them to get the distance to the galaxy. Then observed some of the galaxies Slipher did. So, okay, and measured their distances. When they compared the distances to the redshift, which Slipher has observed, they found that further away the galaxy, the faster was it moving away from us. So if the galaxies are very far, it's basically moving at a faster rate. So it's kind of important that further away the galaxy, the faster it appeared to recede from us. Or some other astronomers have also found similar results. But the work of Hubble was put in forefront. It was considered to be very important. And as we know now, it's true for every distant galaxy that we observe. They all are actually redshifted, all heading away from us. And this ties into what another scientist had concluded, that the universe is expanding. So the scientist George Lemaître, I hope I'm spelling the name correct. That's not his full name, by the way. If you check his Wikipedia page, you'll find the full name. So he himself suggested imagining the cosmic clock running backwards. So you have to understand, running backwards means that we are in today's timeline. If we run backwards, we are going to finally go to a timeline where we can actually start with the beginning of the universe. So galaxies in the sky are getting further and further away from us. But that means that in the past, they were closer together. That's obvious, right? If we run the clock back far enough, and they get closer and closer together, until at some point in the past, everything in the universe was concentrated into a very uber dense thing. It was really dense and tightly packed. Now that is a real weird thought at that point of time. It's hard to imagine everything in the whole cosmos, every star, nebula, galaxy, every atom, electron and proton, all squeezed together in one infinitely dense blob. Now that's what the observations are telling us. The scientists also call this a primeval atom, or more colorfully, the cosmic egg fair. Now this term was given by George Lemaître. Cosmic egg fair, that was the term he used. Now if you squeeze all the energy everywhere into one place, that place is going to be hot when the universe was actually a very, very tiny dot. It would have been unimaginably hellishly hot. Then for some reason, it suddenly expanded violently and started cooling. Now that again sounds very weird. Now imagine the sun and the earth. The speed of light is fast, but this is not infinitely fast, because you see the sun is 150 million kilometers away, and the light takes around 8 minutes to reach earth. So in a sense, you are seeing the sun as it was 8 minutes ago. Okay, let's take another example, the Alpha Centauri, which is 4.3 light years away. That means when we see now the Alpha Centauri, it's actually 4.3 years ago. And something similar is for the Andromeda galaxy, which is around 2.5 million light years away. Now from the light that we see, which has actually left the Andromeda galaxy 2.5 billion years back. So this is actually called the look back time. It's very critical. It's a very crucial tool for cosmology, for observing very distant objects. We can see the universe when it was young. You might think that we could see all the way to the moment of the Big Bang. But then there is a problem. At some point back in time, the universe was so hot and dense that it was the same temperature as the surface of the star. It would have been very luminous but also opaque. As it expanded, it cooled and became transparent. If you look back far enough, that moment in time when it cleared up is as far back as we can see. What does that moment look like? By looking at the physics of Big Bang, the math that describes how matter, energy, space and time behave, astronomers could predict when this moment happened, that means Big Bang, in the lifetime of the universe, a few 100,000 years after the idea, we can actually talk about the look back time. So basically when we're retracing our time backwards, we are considering the look back time. Now using the look back time, they could predict how far away it would have been from us and therefore calculated its redshift. So the light that reaches us billions of years later now should be redshifted into a microwave length. I think this point is not very complicated to understand. When the light that is coming out from distant galaxies or distant stars or distant planets, something which we see is actually a light which has left that planet billions of years ago, and there has to be some kind of redshifting. Now that redshifted light might have converted to microwave wavelengths already, so then it becomes difficult. So in 1965, a pair of radio astronomers announced that they found a signal in their radio telescope that was like a background noise coming from everywhere in the sky. Now they tried everything that could explain it, including scraping out the bird poop inside their radio telescope, in case they thought that that might be causing the change. But the only thing that made sense was that this was indeed the red-shifted light from early universe. So that was the only sense that it made. So obviously there was some kind of signal which came billions of years later from some stars or some earlier part of the universe. Now they had discovered the glow of the firewall left over from the birth of the cosmos. Later in the 1990s, satellite observation further refined the measurement of this cosmic microwave background. I think you must have heard about this, CMB we basically call it. And now it's essentially confirmed this glow was successfully predicted by the Big Bang model. So Big Bang model has predicted a lot of success, and I'm going to just discuss them in brief. And now we will see that basically in some kind of exquisite detail. Whatever is there predicted by Big Bang, the details are already there in real picture now, and many experimental evidences are also there. Now its discovery was a huge step in cosmology, the Big Bang, or the effective proofs of Big Bang. The redshift of the distant galaxies and the cosmic background are not the only confirmation we have. Now the Big Bang model is correct. For example, the model also makes prediction about the element we see in the universe. At first, when the universe was dense and hot, only subatomic particles could exist. So you can see from the image, we don't know at the beginning if there were electron, quarks and antiparticles, but definitely after some time we did have protons and neutrons, and within some fraction of seconds a lot of reaction has already taken place. I think these things I've already discussed before, but this image that we have in front of us gives you a short description of the timeline that we have here. Okay. So we see that the universe at first, when the universe was dense and hot, only subatomic particles could exist. But as the universe cooled for a brief time, they could fuse and form heavier elements. Now the Big Bang model predicts certain abundances of elements, ratios of them compared to hydrogen. And that's just what we see in the universe at large. Also, the sizes and shapes of the largest structure in the cosmos are in line with what our Big Bang model predicts. There's a lot of other observational evidence as well. So Big Bang keeps on predicting a lot of things. So as a matter of fact, I'd like to tell you that please make note of what are the things that Big Bang could predict. Okay, I'll also put up a small write-up on that, but at the same time you can also listen to the lecture and make a note of your own. Sometimes visualizing is much more easy. So galaxies, okay, that's an image of a galaxy. So galaxies aren't actually doing any moving. It's basically not moving. But then it's physically true. The galaxies are all for intent and purposes standing still. The space in between them is where all the action is, and it gets even wider. Now this is true. That means the universe is expanding, but that doesn't necessarily mean that the galaxies are moving away from each other. Now this is true no matter where you are in the universe. From any galaxy, it looks like all the others are rushing away from you. Look back at that. You imagine a ruler. No matter what tick mark you start with, when the ruler stretches from that spot, it looks like the tick marks are all moving away from you. So that is the idea that we have to understand. One of the disadvantages of taking classes is you have your cats. So you can hear to the meows of my cat. So Big Bang wasn't an explosion in some pre-existing space. It was the initial exploding expansion of space itself. Try to understand this idea, okay? It was the initial exploding expansion of space itself. We all have some difficulty with these concepts. Obviously, everyone has a lot of debates on this, but the maths bears them out. So we have the maths, and if we essentially look into all observations, we can make of the distant universe. And in all this weirdness, don't lose sight of the Big Bang picture. So what is the big picture here? That the universe had a beginning and we can see evidence of it. Now, not only that, by measuring how quickly it's expanding, we can use maths to run the clock backwards and determine the age of the universe. So an important point is, what is the age of the universe? So you can see in the slide at the low right corner, 13.8 billion years. So that's the age. So currently the best measurement we have of the age of the universe is 13.8 billion years. Now the Big Bang was confirmed when the background radiation I talked about, okay, the glow of the fireball was detected in the 1960s, and in 1990s it was further confirmed definitely. Now other lines of evidence is supported as well. Using this information, we actually have measured that the universe is 14 billion years old. So that's basically for today a basic idea on why cosmology is interesting, and we are actually talking about the beginning of the universe. So in the next lecture, we'll be going for more technical ideas. For now, I'd like you all to please take a note of this. I'm also going to share some written notes, but that may be later. For right now, you can just enjoy the images and listen to the lecture. Thank you.